You can talk now.
Sound up and down. Group ఉంటే
Good morning, sir. Sir, we'll start in another 5 minutes, sir. 5-10 minutes. So your mic is mute, sir. Rajesh, sir. Yeah. Now I'm able to hear, sir.
Are you able to hear me?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Thank you, sir.
Nice. సురేష్ ఇక్కడ స్టాప్ వీడియో ఉంది కదా మరి ఇక్కడ స్టాప్ వీడియో ఉంది స్టాప్ ఉంది ఇది మ్యూట్ లో ఉంది స్టాప్ వీడియో అంటే నేను మాట్లాడలేనా మరి నువ్వు చెప్తారు కదా ఇది వస్తే ఏమవుతుంది స్టాప్ అవుతుందా అచ్చా ఆనే కనబడ మళ్ళీ వస్తుంది ఇప్పుడు వస్తున్నా ఇది ఇప్పుడు మ్యూట్ లో ఉంది అది లేదు
Okay.
Good morning, sir.
Good morning. Good morning.
Yes, sir. Sir, in another 5 minutes, we'll start, sir.
Okay, I'll wait for 5 minutes.
Yes, sir. Yes. Thank you, sir.
మీ వీడియో ఆపేసాను
సార్లు రమ్మలేదా
సార్
సార్లు
సార్ని మరి వాళ్ళు తెలియదు మనకు.
సార్ బిజీగా ఉంటారు.
మేబీ మీరైతే ఉన్నారు.
ఓకే
ఇదిగోండి, మహేష్ గారు ఉన్నారు, రాజేష్ ఇక్కడ నరేందర్ ఉన్నారు. ఇక్కడ మీది నాకు క్రియేట్ చేసి పెట్టా ఆల్రెడీ. అడ్మినిస్ట్రేటివ్ అవసరం ఆల్రెడీ క్రియేట్ చేసి పెట్టేసిన ఇంట్లోనే. ప్రిపేర్గా ఉన్నాను, కాకపోతే ట్రైల్ వేస్తాను దాన్ని.
ఓకే, లాస్ట్ టు వెయిట్ ఫర్ 5 minutes. టెక్నికల్ డిఫికల్టీ ఉన్నది.
Narendra, I think we will start the session.
Yes, sir, we'll start.
Okay. Is it ready?
Yeah, ready, sir. You can speak.
But I'm unable to see others here.
No, that is okay, no problem.
Rajeshan sir, you can unmute yourself.
I welcome all of you. Our chief pattern.
Yes, sir. I'll.
Okay. Shall I start? Any problem?
Yes, sir. No, sir. I'll start, sir. I'll introduce, sir.
Okay,
then,
right.
Yes, sir. Respected Honorable Vice Chancellor Rahul Bajja, IAS, Dr. Y. Rajeshwar Rao Garu, Administrative Officer, Dr. G. Devaraj Garu, Associate Dean Sciences and Humanities, Mrs. AVV Anupama Sridevi, HOD Mechanical Department, Dr. Rajesham sir, and my dear colleagues and participants. A warm welcome to the short-term course on emerging technologies in the processing of advanced materials and its characterization. The aim of this program is to understand the novel processing and characterization techniques involved while dealing with advanced materials. The demand for new materials of mobile and aerospace sector drives the researchers to investing in the field of materials. However, there are numerous challenges in developing and understand the behavior of such new materials for high-end applications. This short-term course helps you to understand the techniques and thereby evoke the zeal in identifying the suitable methods to explore the limitless. The entire program is scheduled in such a way that there are a total of 10 sessions spread over 5 days with talks from eminent speakers from India and abroad. The speakers are from IITs, NITs, foreign university, R&D sector, and industry. I'm extremely thankful to all the speakers who have generously accepted on goodwill to the invitation to share their knowledge on emerging technologies. I'm very happy to share that we have received tremendous response in terms of registrations from diverse sectors. The participants include industrial persons from industries such as Tata Motors and Sai Deepa Drills, faculty members, research scholars, and students from educational institutions such as IITs, state and central government, and private institutions. The participants are from different parts of India, right from National Capital City, New Delhi, to Tamil Nadu, which includes participants from the states like Punjab, Uttarakhand, Gujarat, Telangana, Andhra Pradesh, and Orissa. Now, I request all the participants to join for this session at least 5 minutes before the scheduled time in our day-to-day, and also be to actively participate in question answer session. At the end of each session, feedback link will be provided, which helps us to improve ourselves in organizing such events in future. Finally,
There's audio problem.
You all have fruitful sessions, which gives you an insight. Yes, sir. I think Rajesham sir got. Yes, sir. I now request the HOD, Department of Mechanical Engineering, Mrs. AVV Anupama Sridevi, to present the gathering. Thank you.
Some technical problem.
Yes, sir. Some technical like net connectivity problem. Minutes, sir. We're just connecting it.
Mahesh sir.
Anupama madam.
IAS. Dr. Y. Rashid Administrative Officer, Mr. N. Narendra, conveners of the short-term course 2021, fellow faculty members and dear the Department of
Sound mute అయిపోయింది చూడండి.
వాళ్ళ సంబంధం ఓకే.
The Department of Mechanical Engineering at RGUKT-Basar strives to improve the quality of education in terms of enhancing the practical knowledge, short-term courses and other training programs. The key strengths of the department are the well-established laboratories with good infrastructure. The faculty members graduated from IITs and supporting. Every year, the department organizes outreach program ITI students with.
Oh, sorry for the disturbance, sir. I think there is some network issues.
The technical
I now request Administrative Officer Dr. Rajeshwar Rao Garu currently address the gathering.
Thank you, Mr. Mahesh. I invite our Honorable Vice Chancellor, Rahul Bajja Garu, and my other friends who are participating in this short-term course. Most of the people are known to me. Either they have worked in RGUKT for some time. I wish them best of luck. And it is a course like this, emerging technologies in processing materials and characterization, will definitely give some innovative ideas to the people working in this field. And such short-term courses are required at least once in 2 months. And we have seen that the materials that were developed in the past 1 decade, mostly the nanomaterials, they have taken, in different fields, they are being used now. So right now the need of the hour is solar cells, the efficiency to be increased so that we'll get solar electricity and solve the energy problem. Like that, there are many other materials which are of importance. Now, one of the important aspects one has to think about is the biodegradation of polymers, especially these plastics which are causing a lot of pollution. I think the members will ponder over such important things. And also, as indicated in the our Science Congress, they want to convert the biomass to alcohol. That is, things like bagasse to alcohol. So all these materials will definitely help us, not only in day-to-day life, they help in the defense field also. The other day I was having a discussion with the directors of DRDO or others. They were saying we have to keep pace with the research that is going on in advanced countries like France, Germany, China, America, etc. We have to keep pace with them. And if the innovation is not done, we will be nowhere. We have to depend on others. So equally, we have to develop the materials and develop them in such a way that we will be competing with in advanced countries. With these few words, I thank the organizers for conducting such short-term courses. Thank you, Mahesh.
Okay. Thank you, sir. I request Narendra to kindly make Ajay Pandey the session speaker as a co-host. I request now Dr. G. Devaraj Garu, Associate Dean, to kindly address.
Respected Vice Chancellor, sir, respected Administrative Officer, and the conveners of short-term course, Mahesh sir and Narendra sir, and all the participants, good morning to you all. This is the first short-term course in RGUKT during this pandemic time, and the conveners deserves appreciation from university. And we thank all the resource persons for having given their consent, choosing a topic relevant to the As we all know, the moral test. So the expertise in mechanical engineers lies in optimizing the parameters to have, in order to have a feasible smart devices both in as per the requirement, market requirement, and defense applications. These days, the research is mostly interdisciplinary. As we know, physicists and biologists working together, physicists and mechanical engineers working together. I read an article very recently. I have seen that biologists and physicists working together developed a protein that binds to a cell. When the protein comes in contact with the parent partner protein in the human body, it makes a contact with the protein. So it forms a covalent bond. So now the research is at a molecular level, like a gluing proteins to one protein to other protein. Now it is a challenging task for a material scientist and characterization labs to develop device techniques to characterize materials at nanoscale. I also learned from the article that there is one research lab in Japan, a silk. So the level of research is molecular and atomic level. These are the examples. And we also recently seen that aerogel, 2.5 centimeter of a cube as a surface area, covering surface area equivalent of one football. So there are many topics like this. They are very interesting, and in the we also have to learn characterization facility compatible and the open platform for the researchers to continue their research. Thank you. My sir, thank
Yes,
you.
sir. Thank you, sir. I now request the head of the department, Mrs. Anupama Sridevi, to kindly address the gathering. Thank you.
Sorry, sir. I welcome all once again to this workshop. Now, coming to the department has MOUs with Non-Ferrous Technology Development Center, Hyderabad, Central Institute of Tool Design, CITD, Hyderabad, and NASCOM QP program in Product Design Engineer (PDE) for the benefit of the students in fine-tuning their skills to make them industry ready. I would like to congratulate the conveners Mr. M. Narendra and Mr. K. Mahesh and the students who are supporting at the back end for their continuous efforts in approaching the resource persons organizing the program in a structured manner. I wish all the participants that this program would help you to improve your knowledge. And finally, I am very pleased to be a part of this program. Thank you.
Thank you, madam. I now request Mr. Narendra to propose vote of thanks for the inauguration session.
Yeah, I would like to thank today's Chief Patron Sri Rahul Boja, IAS, and VC Vice Chancellor RGUKT-Basar for his kind approval and organizing this short-term course. I also would like to extend my sincere thanks to Professor Y. Rajeshwar Rao Garu, Administrative Officer RGUKT-Basar, for his presence at this inaugural session, and also for sharing his important thoughts and ideas about today's short-term course. I also would like to thank Associate Dean Sciences and Humanities, Dr. D. Devaraju sir, for his presence at this inaugural session and sharing his valuable ideas to conduct more such kind of activities in a university. I also would like to thank Ms. Anupama, ABV Anupama Sridevi Ma'am, HOD, Department of Mechanical Engineering, for her presence at this inaugural session. I also would like to thank Professor S. Rajesham sir for his presence uh, at this short-term course, and also would like to thank Associate Dean Engineering Mr. Shekhar Sheelam sir for his presence at the inaugural session. And finally, I also would like to thank all the faculty members from the Department of Mechanical Engineering to extend their support to organize this short-term course. Last but not least, I also would like to thank all the resource persons for accepting our request to conduct this short-term course. I welcome you all to the short-term course 2021 organizing by RGUKT Basar on a topic emerging technologies in processing of advanced materials and its characterization. Thank you all.
Thank you, Narendra. I now take the privilege to invite Dr. Ajay Kumar Pandey, Assistant Professor from NIT Warangal. Narendra, I think you can share. Narendra, you can
Yes, sir.
invite the speaker. I take the privilege to invite Dr. Ajay Kumar Pandey, who is an assistant professor from NIT Warangal in the Department of Metallurgical and Materials Engineering. Dr. Ajay Kumar Pandey has received his PhD from IIT Kharagpur in the year 2011. He has published 18 plus research articles in peer-reviewed journals, including one in Nature Scientific Reports. He has guided 4 ongoing projects, 1 is submitted, and PhD scholars, and 13 MTech students. He has involved in various sponsored projects worth 9.8 crore, which is completed, and 1.3 crore of funding projects are going on. His research interests include bioceramics, powder metallurgy, mechanical metallurgy, and shape memory alloys. I warmly welcome Dr. Ajay Kumar Pandey to take over the session.
Thank you, Mahesh. I hope I am audible and
Yes,
visible.
Yes, sir. Yes, sir. You are audible, sir.
Thank you, Mahesh. Let me share my screen first, then we'll continue.
Narendra sir, you can stop sharing the screen.
Is my screen visible?
Yes, sir. Yes, sir. Your screen is visible.
Thank you, Narendra. Mahesh. It is always my pleasure to be associated with RGUKT-Basar, as that was my past job. So it is so close to my heart. So whenever I get any opportunity, so I try to take. And this time also, when Mahesh requested me, so I readily accepted that. And I thought to give one presentation on something. So as the title goes, so material characterization is there. So I thought I should take that privilege. But on the same side, I was thinking that if we are speaking relatively advanced topics and advanced characterizations on some advanced, very advanced material in the beginning. So that may be little difficulty for the students from mechanical side. So keeping all these things in view, I try to keep my things on basics. I will try to touch upon the basic things, but with a little bit of fundamental touch. Okay, so that without putting much effort, if people can listen these things, so they will be getting benefit. Okay, so that was the whole intention of my designing this course, this lecture. So here, basically, this material characterization is a very vast topic. So it is not possible to cover all things in 1.5 hour time duration. But still, I try to cover few of them. Here, I do not know. I was targeting to tell something like this, means some portion of XRD and some portion of SEM and then some thermal analysis I was thinking. But I do not know means how much time I'll get and all this. So what I'll do, I'll go on. Maybe I do not know, whatever I'm thinking, I may be mostly able to cover up to these two topics with a bit of cut short, means XRD and SEM. Let me see. So what I'll do, I'll try to focus a little bit on basics. If you know it or do not know it, please respond. I want all participants should respond who are listening to me. And anytime, I want it more on discussion mode, because I cannot see the audience now. It is a completely blank screen I am speaking. So I want a response from the participants so that I understand that you are following me. And also I am not disconnected. Many times it happens that the speaker gets disconnected and keeps on speaking. And we do not know that it is like that. So I want that way it should go. So more interactive way, we'll go ahead. Means until you understand, do not let me go ahead. So that should be the way for today's discussion. Before I enter, let me give you one example. After this is okay now, you are hearing me.
Yes, sir. Yes, sir. You are audible.
Yeah. You should keep responding me, otherwise it's a problem.
Yes.
So, what is that? I am starting with one example. Say, I know about steel. Okay. So with some little bit of alloying, I can make it a stainless steel. Up to that is okay. Now, even a stainless steel will have varieties. Correct? So I can have martensitic, ferritic, austenitic, and even I can have duplex steel. Now, how to know? I am giving you a piece of material, then how to know about that, which kind of steel I have. Correct? So it's a big job. So that job we can do by some characterization technique. There you see, if I do not do that, I'll be missing a lot, because all the properties of, say, I am giving some example for ferritic and austenitic steel. You can see the list of properties I'm showing, they are entirely different. Right? We must know their differences in structure to understand, or that there will be a huge differences in properties. But seeing physically or just like that, we may not be able to do so. So what is needed? We have to know the structure. Okay, so I can show you this ferritic structure is like this, and austenitic structure is like this, and we see that there are little bit of small difference, say BCC to FCC. Okay, so much of property changes are coming. So this is true for all materials, right? Now what I have to do, I have to understand what kind of structure a material is having. So to understand that thing, what I can have, I have to characterize, as I said. Two major tools for characterization is XRD and SEM. Now you see, both the tool can tell you something about the phase, or whatever I was telling, which is alternating, what is ferritic in the previous example. See here, I am doing some XRD in this figure. There, after doing the XRD and analyzing, I am able to understand what are the phases are there. I can see here completely some phases are gamma and some phases are alpha. Right? So that clearly helps me to understand that okay, it is a two-phase material I am having. In some percentage of that thing is having gamma and some percentage is alpha. So that is helping me. So that is what XRD can do. In other way, if you do SEM, you will be seeing that this kind of images, and there you see some portion is ferrite, some portion is austenite. So again, it is helping me to recognize the phase. Right now, today I will try to tell you how fundamentally we can differentiate between the phases, how these peaks are appearing in XRD, or how this contrast you can see in SEM. Right? So that will be the key focus for today. Right? So let us move on. First thing, as I said, my total discussion is based on targeting onto three things. First part is XRD, second part SEM, and third part from thermal analysis if time permits. Right? Here I am trying to tell you some of the books who are very popular in this field. So you can take a note of these things and we can move ahead. Right? So let us move in. First part, as I said, we are entering into now XRD, X-ray diffraction. Right? Before I enter, let me tell you something about the wavelength. See, X-ray diffraction, we are using something which is called X-ray. Okay, diffraction of it we are using as our use, but what we are using basically it's X-ray. X-ray is nothing but some electromagnetic wave, right? And you have an entire spectrum here in this slide. Entire spectrum of electromagnetic waves. You know that we have starting from radio wave, which is having a wavelength of 10 to the power 3, to I have this gamma ray, okay, which is having a wavelength of 10 to the minus 12 nanometer or meter. Okay, so that is that various ranges we have in between. I have these things as a visible range. So this is the entire spectrum. So while I am speaking X-ray, what I am speaking a wavelength of this range 10 to the power 10. Certainly you cannot see this, and as you know that this will be having very high energy, right? So we are dealing with such things, okay, who is having something a wavelength of around 10 to the power 10 meter, 10 to the power minus 10 meter, sorry. Okay, so that is the kind of wavelength we are going to use in the spectrum. Let us move on. What I wanted to say, X-rays, we are not only the materials people or characterization people are only not using. X-rays are used in different fields. So many students get confused how this is different, that is different. So I kept this slide here. So here you can see X-rays are primarily used in 3 different ways. Okay, in security, you probably all of you have seen these things in airports or sometime in railway stations. We keep such things. Okay, so they are using X-ray to scan your luggage or baggage. Okay, so that is one of the purpose. Other way, medical people also uses X-ray. Okay, so we say that thing radiography. So this kind of things are probably known to everybody. Okay, so to analyze a fracture or something, which medical people also uses X-ray. Okay, so that is another type of use. Otherwise, we can use for analytics. Okay, we can use for analytics. That is analytical purpose. We use X-ray. Basically, for analytics, we can use X-ray 2 ways. First, as a diffracted X-ray, and And some X-rays we say fluorescence, XRF. Okay, XRF. You can see XRF is X-ray fluorescence. Fluorescent X-ray we can use. Okay, for that also we can have EDEX, we can have WDS. Okay, again they can have some variations. Today I am not going all to this. All my focus is here, only XRD. Right? So all I am not speaking of, I am speaking only one portion of use of X-ray, that is X-ray diffraction. Basically, I am trying to get such type of patterns, and I am trying to understand some of the crystal structure from this pattern. That is it we are targeting today. Right? So we are thinking about X-ray diffraction, not only X-ray. We are thinking something that diffraction of that X-ray means X-ray I am taking as a wavelength, okay, and diffraction of that wavelength we are utilizing for the characterization or for analytics. Up to this is okay. I am audible?
Yes, sir. Yes, sir.
Yeah. You should respond. Keep on responding. That is only fine. So that is the primary things I am speaking. Now I am entering into XRD. Right? See why I need XRD. Okay. First, before I enter, I want to tell you some of the application of XRD. I listed here. Okay. So primarily we use XRD for qualitative analysis. Okay, qualitative analysis. There, what you do, you identify phases. As I was telling in the first slide itself, that what is austenite, whether in some material there is some austenite or some martensite is there. To identify that thing, I can use this technique. So qualitative analysis I can do. Fine. So that is one of the way. Next thing, I can determine the crystal structure even. Not only that, there is two phases. I can understand or I can know the crystal structure of the phase. So whether it is FCC, whether it is BCC, right? So that also I can understand. Even I can, with a careful analysis, I can even tell what is the lattice parameter or how is the angle between them, right? All these things can be told by this careful analysis of XRD. So that part, that kind of things we say crystal structure determination part. Next thing, one of the application is quantitative analysis, not only qualitative. Means there are two phases. I am not speaking like that. I am saying there are two phases and there are 60% A phase and 40% B phase in that. Okay, so that much I should be able to tell. Means I am doing some quantitative analysis. So 60% A and 40% B is there. So that much I am telling, right? Then that kind of analysis also you can do. I said quantitative analysis. We are not stopping here. Further, we are saying we can do some micro strain and micro strain of, say, in some material because of some processing, we can have some strain in that. Okay, that strain, micro strain, how much it is there in some lattice or crystal. So that much also we will be able to understand by this XRD. Not only that, what is the grain size or crystallite size? Typically, if the grain equal to crystal, then I can do these things. So we can say crystallite size. Okay, so what is the size of that crystal? So that also I can determine by this XRD. Okay. Additionally, residual macro stresses, macro stress. This is what I was telling, micro strain. Additionally, macro stresses and texture. Whether a material is having some texture or macro level some stresses are there or not. So those things also will be able to understand. Not only that, we can understand whether some synthesized or developed material is having any amorphous content or not, or totally it is crystalline material. All this thing matters. All this thing matters for the property of a material. So, and we must know, and that's why XRD is a very big tool. Not stopping here, I am continuing further for this application. You can see, we can see the preferred orientation. So how their orientations are there. Additionally, we can determine phase diagrams, so which is a very big or important part for metallurgist or material scientist. Okay, not only that, we can use this XRD for thin films, which is a very much popular and emerging field for study. Most of the things we are doing coatings and all these things to improve the properties, and to understand the quality and the depth or thickness of coating and all this, we are using this thin film study of X-ray. Right there also we have variation. Okay, we can understand the lattice mismatch, we can understand dislocation density, or so many things we can do with these things. Right. So what I wanted to tell, X-ray has a very wide application. Okay, it can tell a lot about material, and hence we should concentrate and learn X-ray properly. Right. So up to that, it is no problem.
Yes, sir. Understood.
Yes, sir.
Additionally, what is good thing with X-ray, that it is non-destructive in nature, so we need not to break the specimen. Okay, so we do not damage the specimen, and a very small quantity even is enough, and it is also relatively faster. Okay, so your scan can be completed in less than 20 minutes, but analysis may take little time, however, but the testing is very fast. Okay, so that part is the strength of this X-ray analysis. So moving on.
A small doubt: how are these all produced X-ray?
How
are these? How is this X-ray is produced?
Let me tell you. In the next slide, it is there. Okay. So
okay.
I'll tell you. Now you see, as you have questioned, the slide is there. So we are producing X-ray. Okay. So here, you know that, as I said, X-ray is a electromagnetic wave. Means it is a wave actually, right? So which is having some electromagnetic part, right? Now you see, if I'm changing the energy of a wave, then some another radiation will come out. You try to understand this thing. What I am trying to tell here, this part only concentrate now. Okay, what I am trying to tell here, I have a filament, right? I have a filament there. Here, this is a filament. Filament, it is normally made of metals. Okay, you know, metals in hot condition can emit electron. Right? Metals in hot condition can emit electron. Now, what I am doing cleverly, I have this filament, I am making it hot, and also I am applying some potential difference. You see, high potential difference I have applied in between them. Okay, high potential difference I have applied. That implies what will happen? Electrons which is emitting out, they will get certain velocity under the potential difference, because they will accelerate. Because electrons, you know, it's a charged particle, and I have potential difference. A charged particle under potential difference will get a movement, and they will accelerate. So they will get some velocity. That implies they will have some momentum, because electrons is having some mass, and then they are in velocity, so momentum will be there. Now what I'm doing cleverly, this very fast moving electrons, I am trying to stop suddenly with some stopper. Okay, that thing I said target actually. So that fellow we said target. Okay, that is nothing but some material who can stop this velocity or movement of the electron. Right, so that part I am saying target material. Now what I have a very fast moving electron, and suddenly it is hitting the target. You can see in this figure, in this one. Here you see I have a filament, electrons are getting emitted, and they are hitting suddenly, which is called target. Right? So they are hitting means their velocity is changing, means almost they are getting zero velocity theoretically, or they are changing their velocity to lower velocity. If they are doing so, effectively they have to emit energy, because while they are in movement, they are having some kinetic energy. That kinetic energy suddenly stopping, so that they cannot stop until they release the energy. Correct? So they have to release the energy, and while they are releasing that energy, they will be releasing in the form of another radiation. Correct? In the form of another radiation, and that radiation, if having that sufficient energy which is falling to the range of 10 to the power 10, then that thing I am saying X-ray. Correct? It can emit any energy, but my targeted energy should be a X-ray kind of. And I have told you, X-ray is having this much amount of wavelength. Correct? So all the whatever this thing is ejecting, or if this thing is ejecting, it is not useful to me. I am thinking X-ray. So I am targeting to have certain energy which is in this range. Wavelength is corresponding to energy only, correct? So they deal together, right? So that part. So then this will be producing X-ray. So let me tell you in one line what I am trying to tell. That what I said, highly accelerated electrons, these fellows. Okay, if suddenly decelerated, I am suddenly decelerating here, suddenly stopping them on impact, because it is coming and giving some impact energy, impact force on. Okay, some of the kinetic energy, because electrons are in movement, okay, is converted into electromagnetic energy. Okay, that electromagnetic energy can be a X-ray. Right? That is how we will be able to produce X-ray. So that is the basic principle. Now we see in reality how we produce X-ray. Right? So same principle we are adapting in the production of X-ray. What I do, I have a filament here. Okay, so that filament is connected to some transformer, so they can give power to that, so that it gets heated up. So once heated up, so that heated filament, that is mostly tungsten, so metal, so they will be able to emit electrons. So once they are emitting electrons, what I am doing, I am giving them some potential difference between this and this, high potential difference. Okay, so then they will be accelerating as these arrows are indicating. Once they are getting accelerated, suddenly I have something which is called target. Okay, this is nothing but anode, and this filament can be cathode. Okay, so because in between them I have potential difference, and that potential difference is very high. If anybody is anybody have seen done some X-ray anytime, they'll be saying we are doing a 30 kV to 40 kV or 50 kV. You can understand. So that is the potential difference, very high potential. It is in kV, 30, 40, 50 or 60 sometimes. Right? So that is very much potential. So these electrons generated, they'll get accelerated and suddenly decelerated, hitting by the target. And as it is shown here, some wavelength will come out, and that wavelength we are allowing to come out through certain windows. Okay, and that is nothing but my X-ray. Correct? So that is how we produce X-ray. This part is clear?
Yes, sir. Clear, sir.
Yeah, sir.
Yeah. Now you see, I have to take some precautions to let the process on. What is the precaution? Here, first of all, what I am saying, that so much of kinetic energy is getting converted here by hitting the target. They are striking the target, and kinetic energy is converting to potential energy. But you know that very fraction of that thing only gets converted to the X-ray. Rest of the things are producing heat. Right? So what I have to do, I have to take away the heat from the target. So for that thing, you'll be seeing a cooling arrangement is there attached to the target. Every target will be having some cooling arrangement. Now, whatever machine you have in Basra, if you see that attached to that, we have a chiller unit. correct? So chiller unit basically does this job only. It is having that big chiller is doing only this job. It is cooling this target. Okay, so that is having nothing other purpose. Only the target it keeps on cooling. Correct. So that is the job. Additionally, what I have to do, I have to let this process on under vacuum. Okay, so to keep these things under vacuum, what we do, we keep everything in a sealed container, and that container itself will vacuum and will seal it. Okay, so that everything happens under vacuum. So that is another thing we have to take care. Okay, for the sustainability. Here I am showing one example how a X-ray source looks like. If you have seen any time your X-ray that is available in Basra, you also have this kind of target, okay, in your machine. So that will look like this, and this is inside is like this only. That has only one job, to produce some X-ray, right? So this is a small thing. That is the producing the X-ray. That is what we say X-ray source. This is okay?
Yes, sir.
So fine. Now we know how to produce X-ray. Okay, now we know how to produce it. So now whether these X-rays are going to help me. See, now I have X-ray and I have told X-rays all people are using, security people, medical people, whether I have any difference between them. Okay, whether the X-ray I am using, it is the same as the security fellow uses or medical fellow uses, or I have a difference. So I am trying to focus. Yeah, what is that difference?
Sir, medical purposes. Sir, sir, for medical purposes, sir, we use it for a human body, no, sir, and for security reasons, we send arrays inside the materials, things.
No, I am trying to understand what is the fundamental difference. Application wise, what you are doing at the secondary, right? So fundamentally, whether this fellow, and you are doing this some X-ray, you are different. All are using X-rays, but fundamentally they are using different X-ray, or it is the same X-ray?
Different, sir. Different.
How do you know that?
So maybe it is the intensity of the X-rays which is used for different applications.
Anyway, let me explain you. Okay, it is not exactly the intensity. There is a difference in the energy. Okay, energy and intensity is little different. Let me explain you will understand.
Maybe difference in the frequency.
As I say, okay, energy is related to frequency. Yeah, little bit of, but they will be in the X-ray range only. You understand? So they will be in the X-ray range only. So they will be near around 10 to the power 10 minus 10. Little bit of, as I am saying that energy is different. So little bit of frequency will be different, but they are very close. So let me explain you how they are different. Okay. So now I understood X-ray can be produced. Okay. Now I am just thinking what question just you posed, that what is the energy? Okay, what is the energy of these things, or what is the wavelength? Wavelength and energy is similar, proportional, correct? So we know that energy and wavelength, say energy and wavelength, you see, they are inversely proportional, right? If I have a high energy, that will be lower wavelength. If I have lower wavelength, automatically higher energy. So that is the truth. So that is we are not thinking much about that. What is my concentration now? Say I have produced some X-ray in the previous slide. Some X-rays are coming out. What is the wavelength of X-ray that is going to coming out? Okay. If I think, try to calculate or understand the wavelength, what I have energy. So that will be converted to wavelength. I am thinking whatever electrons are coming out, okay, all of its kinetic energy is getting converted to X-ray. So complete conversion is happening, right? If it happens, then I will be getting maximum energy converted to these things. Then that implies I will be getting minimum wavelength, right? If I get the minimum wavelength, what will be the size of that wavelength? Okay, so what I am saying, E max means maximum energy is getting converted. Corresponding, I will be getting lambda min, minimum lambda I will be getting. Then what I am getting, so I know that this is a relation E equal to H nu. So nu you can C by lambda. So I am getting E max is equal to Hc by lambda mean. If I do these things, okay, I get that is equal to potential difference. Right? If I put all this value for lambda mean, if I try to calculate, what I get, lambda mean is equal to Hc by E B. E is nothing but the potential charge for electrons, and volt I am applied. So these things I know, these three. Okay, if I put the value of these three, okay, then I get all calculations, and then I get these things. What I say, lambda mean is equal to 12.43 by B. Okay, what I wanted to say here, lambda is inversely proportional to voltage. Right? So proportionality constant is 12.43 I am getting. Right? If I am getting lambda mean, then I have to see the maximum amount of voltage I can keep. Right? So if I go on increasing the voltage, so I will be getting on more smaller and smaller lambda. Right? So in general, rule relation is lambda is equal to 12.43 by B. Now this is the shortest wavelength possible. Okay, these things I was able to calculate, but with the assumption that all the energy is getting converted. But in reality, it is not that case. All energy that is striking, it may not convert. Correct? Sometimes some of the electrons fraction energy will get converted, and then in that case, it will be producing more than that wavelength, or having lesser energy, and more this wavelength will be coming. So in that case, there is a possibility I will be getting some wavelength which is more than that of shorter wavelength. And just think that I will be getting a not only one wavelength, that shorter wavelength, sorry, more than that shorter wavelength, there will be plenty of wavelengths. Because some one electron is having converting 10%, another fellow 15, another fellow 30, another fellow 90, another fellow 100%. Right? There will be plenty of electrons and their fraction is plenty. And hence, what is going to come? A plenty of lambda. Not only a single lambda. Huge amount of lambda is going to come while it is hitting that things. So those things we say white or continuous radiation. You understand? There are two differences. We say shorter wavelength and continuous wavelength. These things you have understood? We say white radiation.
Yes.
White radiation means it's a mixture of lambdas. We say light is a white radiation.
Yes.
Okay, because light is having a mixture of lambdas. Here you see light is having this many lambdas. Right? This many VIBGYOR, entire VIBGYOR is there in for light.
Yes.
So many lambdas. Here also for X-ray, whatever we are producing, it will be having so many lambdas. That's why we say this is a continuous or white radiation. Right? So that XRD is again not useful to me. That XRD is, sorry, that X-ray is not again useful to me. So I am thinking more now. Okay, so what is useful to me? Let me think. Now you see, something I am trying to introduce to you, which is called characteristic radiation. Okay, already I have an idea about continuous radiation. Continuous radiation was when I have thought that fraction of its energy is getting converted. Okay, fraction of its energy is getting converted. So that during that time, the XRD being produced, that thing we have said continuous. Now what I am going to tell is a characteristics radiation. So there what is going to happen? Here you see there is a difference between this picture and this picture. What it is doing? In this one, in the first case, okay, you see that one incident electron is coming, okay, that is radiating some energy and going out. It is not changing much of the structure of this electron. Okay, it is just coming and it is radiating some energy and going out. That can be a white radiation. Fraction of its energy is getting to white radiation. But in this case, you see it is different. What is happening? That electron is coming and it is knocking out one electron from the core shell. Right? It is knocking out. It is one core shell electrons is going out. Now what is going to happen? So while a core shell vacancy is being created, then always from higher energy level to lower energy level, one electron will jump. Once it is jumping, then again that fellow will be radiating some energy. So that will be having some lambda, and that lambda is a fixed lambda. Correct? So it is jumping from one band to another band. So the energy difference in between these two bands is fixed. So one electron, if it is coming from higher energy level to lower energy level, then energy difference is discrete or fixed. And hence what is going to happen in between them, a fixed lambda is going to come. Whatever radiation is being produced, that will be having a fixed lambda. That lambda is fixed for that kind of electronic structure, and hence I can tell that lambda is a characteristics of that atomic structure. Can I tell or not? Because every atomic structure will have different energy level, and if energy is from higher to lower, electron is jumping, then every time that lambda will be different based on the material, but that lambda is fixed for a particular material. That point is understood? Is it understood up to that? Hello?
Yes, sir. Understood, sir.
Yes, sir. That is why I say this is a characteristic of the structure, and that is a characteristic radiation. So these characteristic radiation only I using for my detection or analysis. Okay, this white radiation is not only useful for us, the material. Okay, this white radiation is significant or medical value. But I have to go for a characteristic radiation. Right. Now let me enter this characteristic radiation. What I say, characteristic radiation will be produced if and when that incoming electron is having sufficient energy to knock out one core shell electron. Okay, sufficient energy it should have. So to have that sufficient energy, potential difference should be sufficient, right? So that is why you can see here I am trying to show some combination of potential difference. Here you see I have taken something target as moly, means this target material I have taken as a molybdenum, right? Now you see I have applied different voltage. First one is 5 kV, second is 10, 15, 20, and then 25. Right? These many kVs I have applied. Now what you see, while I am at lower kV, say 5 kV, only I get white radiation. In 10 kV also I get white radiation, because continuous spectrum I am getting. Right? Continuous wide range of spectrum of lambdas I am getting. Here again I am saying at 15 kV, that is also continuous. Right? 20 kV, still it is continuous. I see wide range, so many lambdas are coming in that wavelength range, right? But while I have given a potential difference up to 25 kV, now you see certainly some differences has come. Okay, along with that continuous lambda, I am getting some fixed lambda. This fellow is having fixed lambda, fixed energy. Correct? So this is actually a characteristics radiation. And if I zoom this portion, okay, I turn up here. Okay, there you see this is the characteristics lambda. First one I said K alpha, second one I said K beta. What is K alpha, K beta? I'll tell you. But they are different than that of white radiation. Okay, so this is white radiation, this is characteristics radiation. This is okay. Are you following?
Yeah, sir. Yes, sir.
Okay, so that is
Sir, your voice is not clear.
now.
Sir, yes.
There
It's
is an echo,
literally
sir.
fluctuating, sir.
Let me deal with that. I think there is an issue.
Just a minute, participants. I think the speaker will again join back.
I am audible now?
Yes, sir.
Yes,
Now it's
sir.
clear.
Yes, sir, we can hear you.
Again, I think I don't know. Everybody is having the same problem. Everybody cannot hear me, or some people only.
Yes, sir, everybody having same problem, sir.
Now it is fine, sir. Now your
Now
voice
it is
clear.
fine, sir.
Okay. If it is not, please interrupt. Otherwise, it is a useless thing I am speaking. If you cannot hear. Okay. So whatever, I was speaking something which is called characteristics X-ray and white radiation. Now you see in that I have named something which is called K alpha and K beta. Both are characteristics because they have fixed lambda. Right. Now what is this K alpha and K beta? Let me try to tell a little bit on these things. What I have, you see, when a core cell electron, say I have a cells KLM. Okay, when a core cell electron, say from K one electron has gone, then that gap can be filled from L cell or from M cell or some other cells. If it is there, from there also electrons can come and fill up the gap. Now, if a electron is coming and filling this gap from L cell, lambda L, and if it is coming from M cell, so lambda M will be different because energy difference between these two and these two is different. Okay, and the possibility of filling this gap in K cell will be maximum from L cell, then from M cell. So what we will be getting, most possibly that from L cell electron will jump and fill up these things. If it is doing that, that thing I am telling as K alpha. So one electron is coming into the K cell, okay, and that is immediately from the next cell. That is what I am saying, alpha, alpha, beta, gamma, like that I'll be telling. Okay, so if it is coming from L cell, then it is alpha. If it is coming from M cell, then it is beta. Yes? Speaking something? Right? So beta. So that is why I have termed these things as K alpha and K beta. Now you can see the intensity of K alpha is always better, more than that of K beta, because probability of filling a gap from L cell is always higher than that of that M cell. Hence the intensity of this possibility of these things will be always higher. So K alpha intensity will be always more than that of K beta radiation. Right? So that is what you will be seeing, K alpha and K beta. Now if I zoom further into this K alpha only, okay, I get this. Okay, what I am getting here, K alpha 1 and K alpha 2. Now question is again, then what is K alpha 1 and K alpha 2? You see here, what I am saying, this M cell, okay, or L cell is not only a band, it will be having subcells. For example, L is having subcell 1, 2, 3. Each is having different energy level. Now, if a K cell gap is filled from by a electron which is coming L3, that thing I am saying K alpha 1. If it is coming from L2, that thing I am saying K alpha 2, like that. So I will be getting a complete spectrum of characteristics radiation also. Okay, so that will be like this. So characteristics radiation spectrum. However, my intention is not to the spectrum. Now what I am trying to get, K alpha 1 and K alpha 2. So while a radiation, characteristics radiation is being produced, there will be K alpha 1 as well as K alpha 2. So their energy is different, and hence there will be slightly variation in lambda produced by them also. Okay, that is what you are seeing here, that there is a little bit of lambda difference in K alpha 1 and K alpha 2. Right? So that is what we are getting. Now, with it carefully by the machines or using some filter, I can suppress K beta, because there is a pretty good gap and energy difference between them, and hence using some filter I will be able to suppress K beta while I am getting the characteristics. But still now we are unable to suppress this K alpha 1 and K alpha 2. So whenever you are collecting a XRD pattern, that will come with this kind of radiation mixture. Okay, and corresponding that X-ray pattern, what we are getting, that effect will be there in that X-ray pattern also. Right? So these things we take care mathematically. So after getting the pattern, normally we do treat these things to suppress K alpha 2 or eliminate K alpha 2. We only work with K alpha 1 mostly. So that's why many times while we are representing this X-ray, then we will say copper K alpha 1 radiation. Okay, so like that we will be telling. That implies I have taken target material as copper, K alpha radiation I have used, and that too 1 1 means this situation. So this is 3 L3 to K cell, it has come. So this situation I am speaking. That way we specify that thing. This point is okay.
Yes, sir. Yes, sir. You can continue.
Where is the other student? Only Mohesh is responding.
Yeah, sir.
Yeah. So anyway, I have to go faster. Here, what I am saying, now I have a characteristics radiation with me. So now that characteristics radiation, this thing is characteristics again. So if it interacts with the specimen, okay, so many things will happen. Okay, I have listed here. I am not going into the details of that. Among them, some X-ray will scatter. Okay, from the specimen. Those scattered X-ray, among them, some X-ray will be coherent in nature. Okay, that will take part in diffraction. That's why our characterization tool's name is XRD. D is for diffraction. So X-ray diffraction. So we are using diffraction of X-ray. Okay, not only the X-ray. Okay, so that is why our name is XRD. So let me come to diffraction now. Okay. So here, one thing I think all of you know that I am not going into details of these things. So while sometime constructive and sometime destructive interference will happen in between wavelengths. Correct? While a constructive interference is happening, then it will strengthen, okay, and we'll get a bigger peak. While destructive, I will not get a peak. Okay, that is what happens while a material I am testing. This is my specimen, and sometime this X-ray will make some constructive interference, and sometime it will make destructive interference. When it makes constructive, when it makes destructive, based on that thing, I will be getting some pattern like this. Okay, so whenever constructive interference, one peak, one peak, one peak, one peak, and all rest of the cases it is destructive, hence I am not getting any peak. So how this constructive and destructive interference is happening, let me tell you in a nutshell. Here Bragg's law I am trying to tell basically. Okay, what do you know that I have some atomic plane? I think all of you know these things, so I will not tell much about these things. So what is there? I have certain atomic planes and I have a parallel wavelength. So that is in phase. So while I am thinking about the line A dot, okay, so that is in phase. That is in phase. So while it is coming out, there will be phase difference because there are different layers of atoms. Okay, so who is coming from the first layer, they have no lag. Who is coming from the second layer, they will be having a lag of DEC, this much. Who is coming from the third layer, they will be having this much gap. Who is coming from the next layer, they will be having this much gap. So these things is a phase difference. So this phase difference, if it is okay, it will be equal to n lambda. And if this n lambda will be equal to, Bragg said these things only, means delta will be equal to n lambda. Okay, and this n lambda will be equal to relating to 2d sine theta. This d is nothing but interplanar spacing. These things only this Bragg has told. So Bragg has correlated this phase difference, path difference, sorry, this path difference with these things, this lattice spacing, interplanar spacing. path difference and interplanar spacing was correlated by Bragg, and he said that this 2d sine theta will be equal to n lambda. If it is so, then a constructive interference is going to happen, and hence I am going to get the peak. So that is what Bragg said. I am not going into details. Here you see, oh my God, it is not happening. Sorry. Right, you try to see here. Here you see, I have a variable like this lambda, I have d, I have theta. Okay, so if I try to adjust this lambda, d, and theta, what is going to come? This phase difference. When now you see, I am in a combination where this n is equal to 1. It's a whole number. Then I see after these things, it is in phase. Although they have come from two different layers, okay, after coming they are in phase, because this correlation n lambda and 2d sin theta is following, making this n is equal to 1 whole number. Okay, if it is any other combination, then there, just see, if I alter say lambda, I am changing. See, now it is destructive interference because n value is 0.85. So you see, they are not in phase. Any other value, if I do any other things, say d spacing is changing, so then also it is destructive still because they are not in phase. Theta value I am changing. Okay, theta value I am changing. Then also it is still destructive, not in phase. It will be in phase if and only this n value becomes whole. Say, let me adjust this thing to something. Now you see, it is n value is a whole number. Now again it is constructive interference, and here you see again this wavelength is coming in phase. So this is how this Bragg's law works. So I hope you understand this. Is it clear?
Yes, sir.
Okay. Now I'll be quickly telling. I think my time is getting close. Okay. So I'll be quickly telling when these things you are getting constructive or when you are getting destructive. It's a very big part, but I'm going to tell you very quickly, as much as possible, simplifying the things. Okay, so here you see, I have two type of crystal. This one is what type, FCC or BCC? This crystal is FCC or BCC type? FCC, and this is BCC. So I am just thinking now the layers. Okay, first one you see, I have one layer here of atoms and another layer of atoms here. So if I see the projected view, I have one layer of atom, another layer of atom. Right? This is, I am having FCC. Now while I am speaking about BCC, one layer, another layer, another layer, 3 layers. So I am having 3 layers now here. Okay, so let me think now about the interference, how this diffraction is going to happen. Say I have a D, okay, D spacing is there. Now what I have a one ray, both are in phase. So this is one dot, this is two dot, it is coming and interacting, both are in phase. Now you see, if this path difference, this much, means A, B, C, if it is a whole number, okay, then there will be a constructive interference. Correct? Just now we have understood. So assume that in this combination, I have this A, B, C is equal to this thing, whatever delta, okay, it is a 1 lambda. Okay, so they are making interference. So I'll be getting one peak for that thing. Now, same, I am putting additional atom in this center. So now it is becoming body center. So I have 3 layers now. So what is going to happen? So I have this 1 dot and 3 dot. Okay, in between path difference is exactly half. That implies these things will be equal to half lambda. Correct? This path difference will be equal to half lambda. If this path difference is equal to 1 lambda, then this path difference is equal to half lambda. That is 180 degree. So that is completely against the phase error, and hence they will make a destructive interference. And hence, what will happen if the atomic structure is like this? Okay, for this kind of combination, this 1 dot and 3 dot will cancel each other, and hence I will not get any reflection because of this 1 dot. Right? So what is going to come? Say for this one, this 001 and 002 are in 180 degree, and hence there will not be a 001 reflection. Correct? So those things are, we say, forbidden reflections. So they will not be there. Okay? Completely those things, which reflection is forbidden and which reflection will be possible for a particular crystal structure, can be known from structure factor. So I am not going into that thing, but what I will be telling you, a thumb rule, okay, by which you will be able to just understand from where you can get this pattern. So structure factor, based on that thing, you know that we have this HKL things. HKL is known to all of you, correct? Okay, HKL. So I can have a series of HKL. So whatever, in that, what I have to see, H square, K square, L square, that thing should be a whole number. Okay, for a particular combination of HKL. Okay, whatever possible combination you can think, and that thing should make a whole number of these things. So here, what I can have 1, 2, 3, 4 like that. 7 will not be there only. Here you should understand 7 is not possible, and then all of these numbers will be there. Now rule, I have 3 type of crystal: simple cubic, body center, phase center. Okay, rule in which case this reflection will be possible and which case reflection will not be possible. So that thing, if I see, what you have to calculate, you have to calculate H square, K square, L square. For example, 100 reflection. So H square, K square, L square is equal to 1. Okay, and then for if it is a simple cubic, all reflections should be present. That's why you see for simple cubic, all the reflections are feasible. Right? If it is a BCC crystal, then what is the rule? H plus K plus L should be even. That implies all this even number will be possible. Means 2, 4, 6. See, all this even number is possible for BCC. So if somebody says 100 reflection for BCC, that is a lie. It is not possible. Understand? So 100 reflection is forbidden for BCC. Similarly, 111 reflection is forbidden for BCC. So it is not possible. Somebody is telling it is wrong. Correct? So you should understand. Correct? Now this is how I know for simple cubic all reflections, for BCC HKL even. Now for this last fellow FCC, what is that? H plus K plus L is unmixed. Unmixed means Either it will be all even or all odd. Okay, all even or all odd. For example, 1 0 0. If I take 0 as even, then 1 is uneven, odd. Okay, then this reflection is not possible. Then 1 1 0, then this is also mixed type, so it is not possible. 1 it is all odd, so it is possible. 2 0 0, all even, it is possible. Like that, you can understand which reflection is possible and which reflection is not possible for a particular crystal structure. Right? And if you know these things, okay, if you know these things, which reflection is possible, which reflection is not possible, and from this Bragg's law, you will be able to easily find out, you know, a particular lambda. Say if you have copper radiation, then you know the lambda for copper. If you know these things, you will be able to easily calculate this D value. D and HKL has a direct relation. Correct? So if I know HKL, then I'll be able to calculate D value. Like that only people are calculating this D. Right? So whatever, this is one part or implication of this XRD. So here, what you say, what you do, simply you have a X-ray. So that thing is monochromatic. Monochromatic means single lambda you will be using. That characteristics X-ray you will be using. So you have a sample in between. Okay, in that sample there will be several crystals. There can be several orientation for that. When for a particular combination, if crystals are obeying this lambda is equal to 2d sine theta, at that time this constructive interference is happening and you are getting a peak, right, from the detector. So that is what a X-ray does. This is okay.
Yes, sir.
I think I'm not X-ray. So I will almost over. I was very attention. If you have no process, if I have question, I can discuss calculus. Any questions you have?
Sir, maybe in another 15 minutes we can.
Yes, I conclude now that I start that is the part 2.
Sir, your voice is
Sir,
not.
sir, your voice is breaking.
Sir, your voice.
Sir, adjust your mic 1 second.
Now I am audible.
Yes, sir.
Yes, sir. Yes, sir. You
Yes,
are
sir.
audible.
I don't know what happens after a certain time. Network jam or whatever it is. Yeah, please. I am unable to hear. Are you hearing me?
Yes, sir. Yes, sir. You are audible now. I think the student might be saying yes. You're audible.
Yeah. Then what shall we do? We'll stop here or we'll start another thing, but that takes a little time because it is a SEM, again fundamentals will come.
Sir,
We have
someone
another
can
15
give a
minutes,
short
sir.
summary about today's session, sir. Tomorrow we can start new topic or after.
Mahesh, it is your call.
Fine, sir. Then I think we'll stop here because we had a detailed discussion about the XRD. So I thank Dr. Ajay Kumar Pandey, sir, for giving insight details about. See, we all know how we generally get an XRD and all, but the physics behind it and the concept behind how X-rays are generated and how do we quantify has been detailedly explained by the resource person, Dr. Ajay Kumar Pandey. So we are very grateful to you, sir, for accepting our invitation and giving such a insight details about the characterization technique, especially focusing more on XRD, where which is very important for people who are doing characterization. And we are very thankful and grateful to you for spending your valuable time and giving an insight knowledge on XRD. Thank you very much, sir.
Thank you very
Thank you,
much.
Mahesh. And I thank all the participants who has the patience to listen all these so much of fundamentals and details. So normally that is a bit difficult to have 1.5 hour lecture on the around 75 minutes lecture. So anyway, thanks having patience and being there up to the end with all these network difficulties. Thank you all of you.
Thank you, sir. Dr. Rajesham, sir. Sir, am I audible to you, sir? Okay, dear participants. So this is for today's morning session. So a feedback link has been shared in the chat box. I request all the participants to kindly fill the feedback form. I request Narendra sir to kindly share it to all the participants in the chat box to everyone. So thank you, participants. So this is the end of session 1 morning.
Brother, that is a LinkedIn share link. The link in the chat box.
Okay. No issues. We'll get back to you. Maybe in WhatsApp group or in the Telegram group, we'll be sharing the feedback link. And I request all the participants to fill the feedback link.
Yes. Thank you.
Sir, can we get the PPT?
Yeah. Based on the we will share all the PPTs at the end of the course, short-term course. Okay.
Okay, sir.
Okay, sir. Thank you, sir.
Thank you very much.
Thank you, sir.
Yeah. So I request all the participants to kindly join at least 5 minutes before the session so that it becomes easy for us to look into the technical issues, if at all any.
Sir, is there any
Okay,
sir, is there any qualification limit for this sessions?
Not exactly.
So I mean that only 12 plus 10 plus students may listen this session, or sir, anyone who has the interest can.
As such, we have given the registration link. So whoever has registered, we are providing them the link to listen to these sessions, because these are basically a course where we expect the students to understand.
Yes. So basically, I'm from pre-UC 1 student, so I just have the interest, so I'm just listening it.
Yeah, no issues. So as long as any student is having interest to learn and explore the things, they are always welcome.
Thank you very much.
Yeah, thank you. Any more clarifications for the participants?
Can we have the
Fine,
WhatsApp group in a Telegram group, sir?
Sorry?
Can we have the WhatsApp group link in Telegram group?
Okay. I think Mr. Narendra sir would be looking after it. Okay. We'll do it.
Sure, sir. Thank you.
Yeah. Thank you, one and all. So let us meet in the afternoon session at 3 o'clock. Thank you.